Welcome to our SGP Proxy Primer on program pyrolysis, or Rock Eval, going by the commercial name. For those of you who might be new to SGP, we're an open community-oriented research consortium that seeks to address questions of environmental evolution across Earth history through statistical analysis of the sedimentary record. And this, basically, we're focused on two things. One is getting a large database of sedimentary geochemical samples with appropriate geological and geochemical context information. We've now amassed a phase 2 data set with over 109,000 samples, 3.8 million analytical results, and this has been built by the greater than 150 people on the collaborative team. And if you're not involved, we'd love to have you be involved. Please check out our informational website or our search website. The second aspect of SGP is not just building a big database, but learning how to better interrogate that, either through better statistical analysis or better understanding of these geochemical proxies. And a lot of that comes down to teaching our community better ways to do things. And so as part of that, we've started this Proxy Primer series that I'm very delighted to have Dr. Alex Zumberge talking in today. So Alex did his BS at UT Austin, then went on to do his PhD at UC Riverside, working with Gordon Love primarily on neoproterozoic biomarkers. And I'm really excited to have Alex talk to this group because he kind of bridges the industry academia divide that sometimes exists based on his work in both fields. Alex comes from what you might call organic geochemical royalty. So GeoMark is a family company. Alex started off working there in 2012 as, I believe, a technical service analyst, which I'm not sure exactly what that means, but I presume operating the equipment and so forth. He then worked up to his current position as Executive Vice President of Operations at GeoMark. GeoMark, as Alex will tell us, is one of the biggest organic geochemical companies in the world. I don't want this to be too much like an infomercial, but I'll just say that we have run hundreds of samples with Alex and his team at GeoMark. We're all great, Brian Jarvie and so forth. And I've really appreciated both just the personal aspect of working with them and the really high quality data that we get back. And so if you're looking for these kind of analyses, I can personally say that the GeoMark is really the place to go in my opinion. So with that introduction, Alex, why don't you take it away? And thank you so much for talking with our group.
All right. Thanks everyone for having me, and thanks Eric for organizing this. Make sure everyone can see my screen. We good?
Yep.
Okay. All right. So yeah, today, talking mainly about an introduction to program pyrolysis. I did, as Eric mentioned, just to give a quick sort of who we are, who GeoMark is. We'll not spend too much time on this, but we're essentially a geochemical lab, commercial geochemical lab. We kind of have our hands in a few different things, whether it's database products. This is just a map of our global data set of geochemical data, whether that's rock geochemistry or fluid or gas analyses. We have a few different physical laboratories where we focus on a few different specific analyses, whether it's PVT, mud gas isotopes, or gas comps. Our oil lab here in Houston, where we do a lot of biomarker and carbon isotope and sort of oil characterization analysis. And then, of course, our rock lab, where I'll talk a lot about today, where we do all these TOC and program pyrolysis measurements. We just kind of give again a broader scope of who GeoMark is. Kind of just verbally said that, but across our different divisions, we're routinely performing a lot of these services for oil and gas operators. These days too, we're getting into some of the CCUS fields and sort of how we can apply some of these instrumentation and databases to sort of the same data and the same instrumentation in a different lens and a different light. So again, a lot of different techniques and methods and offerings we have based on what the question is, what our clients and our operators are working on. We'll focus today on predominantly TOC and program pyrolysis. And so, as an outline for the talk today, really heavy on, again, program pyrolysis. We'll do some introduction and definitions, a brief history from other industries as well as oil and gas, look at specifics into the instrumentation itself, some of the methods we can employ, and then of course the outputs, the data sets we're getting, and then of course, how those can be applied in a number of different ways. So starting just, at the foundation, right? What is pyrolysis? Very generally speaking, it's decomposition brought about by high temperatures. Typically, it's in the absence of oxygen. You don't have to have a completely inert atmosphere, but you want to minimize any oxygen, because if you did have oxygen, you could sort of oxidize your samples and sort of lead to unwanted secondary products during that decomposition step. When we think about pyrolysis and industry application, I learned quite a bit just researching, how pyrolysis is used across different industries. So whether it's waste management, decomposing waste into different fuels like biochar or bio oils, or in the chemical industry, very common to sort of use pyrolysis as a technique for sort of feedstock applications, where you're breaking down more complex compounds into simpler building blocks, which then you can use this carbon black production, or extreme pyrolysis, where you're making this fine powder and reinforcing, tires and rubber and plastics. And then of course, in my world, the oil and gas industry, program pyrolysis really is an important tool for the analysis of these organic rich rocks to evaluate hydrocarbon potential, source rock quality, and thermal maturity. And you'll kind of hear me harp about those three things throughout the talk. So maybe more akin to this crowd and the academic world for sure. Again, at its heart, program pyrolysis is a hydrocarbon evaluation technique or tool. And really we get these three pieces of data, right? The quantity of organic matter, the quality or the type, type 1, 2, or 3 kerogen we talk about a lot of times. And then of course, thermal maturity of organic matter. And I'd take a guess that no matter what field or research you're doing, if it's geology related, these are going to be important to some aspect, right, of your research. And again, larger picture, whether it's in industry or in academia, these are the things we're sort of evaluating and thinking about. Program pyrolysis is one step, one data set that can help with some of these interpretations. And we'll see again how it's applied and across different data sets, and how it can be used in tandem with other data sets to sort of strengthen your story and your interpretation at the end of the day. So the first thing I want to mention is Eric's guilty of it. I'm guilty of it for sure. But Rock Eval is really a Band-Aid term, right? It's the Rock Eval instrument and equipment has sort of had market dominance since the 70s or so. And so that's why everyone says, TOC Rock Eval or Rock Eval pyrolysis. But just important to know that Rock Eval is just one instrument from a certain company or institute that developed that instrument. So really, program pyrolysis is the technique, right? And Rock Eval, and I'll talk about Hawk today as well. Those are the instruments that employ that technique. So just a few pictures of, this is from our rock lab, where we have a few of the Rock Eval systems. You can tell this is the Rock Eval 6, so 6th iteration. There are some more and less popular ones. The Rock Eval 2 was used for a long time. Don't really know about the 3, 4, and 5, if that was commercial or not, but kind of the more commercial ones were the 2 and the 6. And now I think they've, within the last year or two, have developed the Rock Eval 7. So one company with one offering. Hawk is another offering from a different company called Wildcat Technologies. So just a different instrument, fundamentally the same thing. We're doing that hydrocarbon evaluation via program pyrolysis. So a few different offerings. So, and I'll be guilty of it during the talk too. I'll say Rock Eval. I guess the takeaway is that, again, Band-Aid term, what we're really talking about is program pyrolysis. And I wanted to mention too, we oftentimes, right, when we talk about program pyrolysis, we also pair that with TOC, total organic carbon analysis. And so very little, times when we get requests to run pyrolysis, it's not just a standalone thing, 9 times out of 10, it's TOC and pyrolysis paired together, or TOC first, and then depending on the results, run pyrolysis on those more organic rich samples. And so, TOC can be measured on these instruments. There is a way to grab that measurement and think about that organic carbon that's in your sample. But typically, more times than not, it actually is measured on a separate instrument called this LICO. And then at the end of the day, the two data sets are paired together. And so just a quick detour into this TOC differentiation between Rock Eval and Hawk TOC versus LICO TOC. So with a Rock Eval or Hawk, it is a bit more of a qualitative determination. So you're not directly measuring the weight percent of the TOC in that sample. In a Rock Eval and Hawk system, really it's a kind of determined or calculated value based on the sort of the two-step pyrolysis phase and then residual carbon phase. And so during that the ramp, the temperature ramp inside the instrument, you're first pyrolyzing, and then later at higher temperatures you're going through an oxidation step, and you're relying on this infrared detector then to again sort of interpret and determine the TOC versus mineral carbon, which can be a little bit less confident or cause a little bit more error. And so again, it can be done, but because of some of these caveats here, most labs and for sure in industry, most labs recommend doing TOC on a dedicated LICO instrument. And so the LICO itself is much more of a quantitative determination, and the biggest difference is this first bullet point here. So on Rock Eval or Hawk, there is no prep step there. You're just taking that rock right into, or that crushed rock, that powder, into the instrument. The LICO TOC, however, we're first diluting that crushed rock with an acid to remove that mineral carbon, that inorganic carbon, right? And if it's an important step, because if we didn't do that, then that sort of gets folded in and would overestimate your organic carbon. And so in the LICO instrument, we're combusting here, and that evolved CO2 is measured. Very importantly, the results are reported as a weight percent TOC. And again, just from our experience and the operators we work with, LICO is considered a bit more reliable compared to TOC, to Rock Eval and Hawk. So know that you can get it from those pyrolysis instruments, but typically it's acquired on a dedicated instrument. And that's not just GeoMark, that's other labs too as well. Actually, to put some context behind this, we run thousands and thousands of TOC pyrolysis measurements a year. I'd say probably less than 10% is a request for TOC from Rock Eval or Hawk instrument itself. More times than not, it's from this LICO instrument. So just a little virtual tour of some of our equipment. Here's the LICO. So obviously a bit bigger of a machine and more of a footprint compared to the Hawk or the Rock Eval. But again, it's doing that more direct sort of weight percent TOC output at the end of the day. So a little history of program pyrolysis. I thought this was nice to have some context through as we talk about the different data sets and the different methods and applications. So in industry, pyrolysis have been employed since in the 1960s. Again, really, we're trying to understand that hydrocarbon generation and source rock potential or source rock properties. The Rock Eval system was developed in the 1970s by the IFP, the French Institute of Petroleum. And so really this was a breakthrough technology and a very, very much a step forward in how we think about source rock characterization and reservoir characterization as well. And so, some key parameters that I'll for sure touch on and define later, but TOC, HI, hydrogen index, oxygen index, and Tmax. with respect to source rock evaluation, right, this system, this Rock Eval, became such an essential tool for evaluating these hydrocarbon systems or these petroleum systems. And so really, you know, it allowed geologists to sort of have a lot more data at their hands and a lot more you know, support of some of the interpretations they were making based on, again, the outputs from these instruments. So of course, through the years, we see advancements in technologies and techniques. And so, you know, people would take a front-end pyrolysis system and then pair it with a back-end gas chromatograph or GC mass spec to again get a bit more context and get a bit more detail of those compounds and right, those products of the pyrolysis. And so for sure, I want to acknowledge that there's this whole sort of offshoot talk we can do for a whole nother hour, which we won't today. But you know, PyGC, PyGCMS, hydrous pyrolysis is a common one. And then I did my PhD work on hydrogen pyrolysis on a HiPy, where we're, you know, flushing hydrogen through the system and cleaving kerogen-bound markers at very high temperatures. And so, et cetera, a lot of ways people are using pyrolysis as a front end, right, sort of extraction technique to some extent, paired with some sort of more advanced detector on the back end. I just want to point that out, but today, again, we're kind of sticking with the basics of program pyrolysis in the eyes of a Rock Eval and a Hawk. So it wasn't until really about 2010 that you know, the guys at the IFP had any competition really when the Hawk pyrolysis came out. So Hawk does stand for hydrocarbon analyzer with kinetics. You know, it was a kind of a step forward with the instrumentation itself and how you operate it and how it's maintained and upkept, but also offered a bit more of improvements with respect to sensitivity and resolution. And so, again, we're all guilty of it, that Rock Eval is such a band-aid term because it had sort of market dominance for, you know, 40 or so years, with a few other options along the way. SRA was another one, source rock analyzer, that's not really offered anymore. Nowadays, again, it's mainly either Rock Eval 6, Rock Eval 7, or the Hawk. And so, again, moving sort of now to modern times, right? Very important tools in basin modeling and exploration specific to the oil and gas industry. And so, you know, these are some of the first measurements you're doing when you go take a core, or when you're drilling a well and you get all your cuttings. TOC and pyrolysis are sort of the foundational level of your analyses before then you sort of split off and do a whole lot of other potential analyses. And so very much a fundamental tool for characterizing source rocks and evaluating their potentials as hydrocarbon reservoirs. All right, so just going to spend some time now just specifically talking about Rock Eval and then Hawk next. So again, commercial sort of versions of the Rock Eval system, Rock Eval 2, which is now more or less obsolete as of a few years ago. We have a few Rock Eval 6s that we use quite often. Rock Eval 7 is a newer version. Again, I think it's just as of the past year or so. I know there's an emphasis on sulfur in this instrument. We do not have one, so admittedly, I do not know too much about it. But just know that, you know, these are some of the newer or more common 6 and then newer offerings from Rock Eval. So the expectation is you have this, you know, nice sort of low footprint, instrument in your lab, and you load it up and you run and it's worry free. But really, as you saw from the first pictures, the reality is that, you know, I don't even know if we know where our side panels are. The Rock Eval can be a bit more complex and problematic when we're talking about, at least from a commercial point of view. So we rarely have the panels on because quite oftentimes we're having to go in and tinker with something or make some adjustments on the internals. Doesn't, you know, it is what it is. It's kind of quite common knowledge with this. And so I think the Rock Eval 7, I think, made some advancements on that front. but from our experience, it's just a bit more attention when running and operating the Rock Eval 6. I showed or talked about the Rock Eval 2. This one, again, nowadays is essentially obsolete. We have a few of these around. You can see, older technology and differences in just the interface itself. Still no panels because we're oftentimes having to get on the internals and mess with things. But there are some operators that are if they have old data from Rock Eval 2 and they're drilling a new or looking into a new acreage or whatnot, they want to kind of have the same data from the same instrument. And so we'll keep this around, but very rarely do we run this. More so routinely is the Rock Eval 6 and then the Hawk on the other end. So to give you some ideas of again, run times and methods and sample throughputs, typically, if we're just doing pyrolysis only, it's about 30 minutes a sample. If you want to add on that TOC option to it, the pyrolysis run ends, and then you have another 30 minutes for that TOZ acquisition, so about an hour total. The sample tray holds about 48 samples. Again, though, this is not one that we're going to kind of load up on Friday and let it run over the weekend. Usually, you got to be there to babysit a bit more and have a closer eye on it while it's running. Across the board, whether it's Rock Eval or our Hawk systems, we run our standards and duplicates every 10 samples, very important. And then the operating conditions, these might not mean anything right now, but S1, S2, S3, I'll define later. These are essentially the outputs and the conditions at which we're measuring those outputs. So S1 is acquired at 300 C with a 3-minute hold. S2 is a ramp from 300 then to 600 at 25 a minute. And then S3 is between that 300 and 400 mark. So over to the Hawk system. Again, Hawk is basic offering for more just routine S1, S2, S3 Tmax outputs, but they also have a Hawk PAM option that I'll talk a little bit about. So I pulled this from the website. Here's the expectation, and then in our lab, pretty good. Again, the Hawk, I think, was made to address some of those issues from the Rock Eval 6 because they just didn't have a lot of competition and they sort of owned the market for such a long time. The Hawk itself, again, it's a little bit more of a compact system. You can notice the robotic arm there and the larger sample tray. Same runtime, nothing different with 30 minutes for just pyrolysis only or an hour for both. But this is one where, much larger sample tray. We can load this up on Friday, program the batches, make sure we're putting in the standards and the duplicates every 10 samples, and we let it run over the weekend. And right, more times than not, it's good to run by itself, sort of a lot more automated, and we're not having to get into the internals and mess with things. So more or less the same conditions when we acquire the S1, S2, S3. I think maybe a bit higher here, going to 650 instead of 600. And again, I'll define those so they make a bit more sense as we go through it. So for sample prep, when we're running either a Rock Eval or a Hawk for program pyrolysis, it's pretty simple. There's not much to it. You take your rock. We don't have anything fancy, just mortar and pestle, grind it down to that 60 mesh, weigh out about 100 milligrams, and add it to these little crucibles, pack it in, load it up, program on the PC the batch that you have and all the information, the weights and the sample IDs and whatnot, and then you kind of you set it and let it go. So no spiking, not very complex. It's pretty simple sample prep. So the method itself now, when we think about the heating programs and the data acquisition, so here's the terms I used before. I'll just kind of flash them again for reference so you know what we're talking about. So right, generally, imagine the instrument's heating up. It's going from room temperature up to 300 and holding at 3 minutes. So as that instrument is heating up and the sample inside of it is heating up, those organic compounds will start to sort of undergo that thermal decomposition, right? Helium is used as a carrier gas in that process. Again, this pyrolysis, this is in the absence of oxygen. And so that's why there's a 2-step and it takes an hour long. If you are going to run TOC and acquire TOC on the instrument itself, after that pyrolysis ramp and hold method has completed, then it switches carrier gases to air to then oxidize the sample and go through that. And I'll explain a little bit more there. So, right, first principles, those high temperatures are breaking down those complex organics, smaller compounds. You're then having evolved gases and VOCs that are swept through the system, and the detector here is a flame ionization detector, FID, measures that sort of the quantity of those released gases. So calibration for sure is important. Right, you guys are all familiar with upkeep of your instruments and sort of repeatability and standards and checks and whatnot. So there's no like in carbon isotopes, the VPDD or whatnot, there's no kind of international standard. Every lab has more or less its kind of own lab internal standards. There are some official ones from USGS and IFP, and we have those and we use those. But quite often it comes down to what you have at hand, and if you do have your own internal standard, you're just calibrating it to these sort of more widely used and available rock standards. I know Jet Rock is another popular one. So the standard, of course, determined from this calibration curve to pure hydrocarbons of varying concentrations. That allows you to, again, build that calibration curve with good repeatability. And standard, just from us, and I know other labs as well, typically it's about every 10th sample is when that standard sample is run as an unknown to verify that calibration. So if we start to see wiggle or wobble away from the standard curve, then we sort of go back and rerun those samples or tighten it up and rerun again. So repeatability, again, we'll look more into what these terms are, but Tmax is about ±2C, and then 10 or 20% variation from the S1, S2, S3 peaks. Okay, so I've been talking about S1, S2, S3. This is actually what it looks like when we talk about what's called the pyrogram here. And I'll sort of again stress why these are important. This, of course, is just a cartoon, but you get the idea of y-axis is concentration from the FID detector versus time and temperature here. So as the method starts and the temperatures start to increase, you get your first S1 peak, then your S2, and then S3. So the data itself is obtained from the instrument and it's processed and interpreted internally. Again, using that standard calibration check, very important. It's then reporting the relative concentrations and then the time and temperature on the x-axis. So, results and digits are reported in Excel and accompanied often by this pyrogram. So pyrogram is, again, just kind of a generic cartoon here, but this is a very important piece of information when you're looking at program pyrolysis data. You always want to also, not just look at the digits, you want to look at the pyrograms as well. And so this essentially is just a spectra or a chromatogram, however you want to think about it, that displays those relative abundances of those compounds for those different peaks at the different temperature ranges. And we'll go through, look at some real data from that as well. So again, more into the outputs themselves, right at the heart of the method and the experiment here we're doing, pyrolysis kind of simulates natural maturation, right? So on geologic timescales, you of course have lower temperatures but much more time, and you get the oil generation and expulsion. But on present day timescales, because we don't have that time, we essentially heat up the sample to higher temperatures and sort of use it as a proxy to then compare against what we see in the natural world. So the outputs, again, that I've been talking about, S1 is that first peak that's evolved, and that's what we call the free hydrocarbons or the free oil content. And so again, on that, it's relative to that concentration on the y-axis, and so and we know the weight of the rock that we put into the sample. So the measurement or the units is for S1 is milligrams of hydrocarbon per gram of rock. S2 is what's known as the remaining generation potential of that rock, so the source potential. Again, also milligrams of hydrocarbon per gram of rock. Tmax is very important, and I'll show a number of reasons how we use Tmax and why it's important. But this is the essentially on that x-axis, this is the temperature at which that S2 peak reaches its maximum. And so at the apex of the S2 peak, draw the line down to the x-axis, and that'll give you your temperature. That's your T max, it's called. And then S3 is another value. This now is the organic carbon dioxide yield, not in hydrocarbons, but this is milligrams of CO2 per grams of rock. So now you kind of know what, the main things we're measuring with program pyrolysis and the main outputs and deliverables. These are just some, again, you look into any, organic geochemistry book or whatnot, you'll sort of have some ranges of values of typical S2 outputs, and then how you can kind of classify that source rock potential. I will say that these are from more of an immature petroleum system. And so these are not hard values by any means, or the goalpost kind of moves depending on the maturity of the rock you're looking at and the kerogen type. And so, but to give you an idea of some of the raw digits and the outputs of S2 specifically, these are some of the ranges in which we kind of can classify the potential for any given source rock. So, right, classic Green River Shale has values of S2 of 100. Eagleford, a world-class producer there is value of 15. Humic coal, right, for more of a type 3 kerogen, very overworked and has very high values. And then really the average shale, is less than 2. So negligible to poor on that sort of source rock potential. But again, these are just kind of very much guidelines, not strict rules. We pair S2 oftentimes with T max as well. So again, T max is the point at which that S2 peak reaches its apex, its maximum. And so this top plot here is very generalized T max ranges, and sort of when we think about the oil window. So from immature black oil, the more mature your source rock is getting, the more the more alteration, right, to those hydrocarbons, to eventually you just get it down to the simplest component, methane, CH4. So the T max and therefore the S2 behaves differently depending on your maturity. And so this is sort of the first look at of how we can interpret from pyrolysis data. We can interpret a maturity, thermal maturity from the rock you're looking at based on this T max value and these windows here. And then this bottom plot here shows a bit more specific Tmax ranges for type 1, type 2, type 3 kerogens. And so obviously, again, you can sort of discuss this at length if we want, but the different types of kerogens, of course, have different hydrogen to carbon ratios or oxygen to carbon ratios, and that changes their sort of systematics of how the oil is generated and expelled. And so type 1, for instance, has a much narrow window in that oil window, only 8 degrees or so in Tmax, versus much wider windows in type 2. But again, this is your first instinct, or your first look at, or first sort of hint at what the maturity of the rock is that you're working with. Okay, so from those raw outputs, the S1, S2, Tmax, and whatnot, we sort of a number of different collaborators and researchers have gone behind this to create these ratios that are very useful. And so there are, there's a few more than this technically, and if you get a pyrolysis report, you might see a few more columns, but these are the ones that I often look at it and sort of scrutinize the data with. So hydrogen index, essentially we're taking S2 over TOC, oxygen index S3 over TOC, normalized oil content is S1 over TOC, and then this production index is just S1 and S2 together. And again, now we're looking at the main outputs, S1, S2 peaks relative to TOC. So that's often why, again, like I said, we pair pyrolysis measurements with a TOC analysis as well. Very, very rarely do you just analyze it standalone. You could, but then you lose the potential to do some of these more derived ratios that have a lot more sort of interpretive backing and history behind them. And so spelled out ratios right here. and then a bit more context of what each of them mean. So the hydrogen index is that normalized hydrogen content of the rock. And so this is where we start to think about both maturity and kerogen type. And so typically type 1 kerogen is going to be hydrogen rich. Type 3 is really hydrogen poor, that reworked kind of humid coal system, right? And type 2 is, you know, the classic marine shale, where that's kind of intermediate between the two. Generally, general trend is that with increasing thermal maturity, your HI values will decrease. Oxygen index is now, instead of hydrocarbons, it's the normalized oxygen content. There's a number of different sort of derivative interpretations you can do from the OI. Typically, if you have low TOC systems, your OI might be a bit meaningless, more or less. Normalized oil content, this is important too. This is that S1 over TOC. So this is used to identify reservoir rocks or the thermal maturity of tight source rocks. So again, in my world, right, we're often thinking about a source rock that is generating oil, and in a more conventional system, that oil is expelled and then sort of ends up in a reservoir rock, a porous sandstone, for example. And so we wouldn't expect that porous sandstone to have a lot of kerogen potential, right? It's all fluids that have been migrated in. So in those examples, you can identify reservoir rocks from really having, you know, high S1. At the same time, you can apply it to more of a tight source rock as well. And oftentimes, you know, we'll use this ratio or this normalized oil content to think about contamination and what we call oil staining as well. So again, tying back to maturity, typically a mature rock will have a higher S1 over TOC compared to immature. And then again, reservoir rocks where that fluid has migrated in and occupied the pore space will have higher ones as well. So contamination can be an issue, and I have an example to show that. But again, S1 is your most mobile, your free hydrocarbons that are not sort of locked in that kerogen. They're freely moving throughout the pore space there. And last is the production index. So this is the S1 over S1 plus S2. And so with this, right, sort of indicative of your conversion of kerogen into those free hydrocarbons. So again, tying back to maturity, typical trends is that with increasing thermal maturity, your PI will increase. And then, you know, again, when we think about contamination and overprint and what to look out for, typically if you have like low TOC and very, very high PI, that's kind of a red flag to where, okay, we're looking at a contamination from some sort of drilling fluid, oil-based mud or whatnot. Again, because this is only looking at S1 and S2 peaks. Okay, so front end now, that was kind of the crash course into the basics behind the instrumentation itself, the different offerings, the sample prep and the runtime, the operating conditions and the outputs. Now I'm going to switch gears and we'll do a little bit more of the applications from a few different examples. So this is in this application of pyrolysis, we're estimating thermal maturity. I pulled an example from the Niobrara formation. So this is the top of the Nile in the Powder River Basin, Montana up here, Wyoming here. So this is one of the, a very popular petroleum system for oil and gas operators in the US. And this map is showing here, this is maturity converted from Tmax. So again, in sort of basin evaluation or petroleum system modeling, one of the first things you do, whether you have a number of cores throughout the area or again, cuttings from wells that you're drilling, is you start to build these profiles just from Tmax. Pyrolysis is relatively cheap and fast compared to some other alternative analyses. And so by no means is this the end all be all, the final answer of anything, but this helps you set the stage. And you can see kind of, the colors here indicate the different maturities. So colder blue colors, we're kind of in the 0.6, very immature to early oil window, 0.7, 0.8. And then the greens here indicate, more of the top of the middle of the oil window, 0.9, 1.0 RO equivalent maturity. And so again, you wouldn't sort of only do these maturity maps from Tmax from pyrolysis and then go and start to evaluate or explore. You want to pair it with other things, but this sort of sets the stage for additional analyses. So the other, now you can take a bit more of a detailed approach and do actually measured RO, measured vitrinite reflectance, a bit more intensive, a bit more expensive, longer to do. But you can see now how that sort of, the idea of that is changing, or the view of the basin is changing. And then, ultimately one of the end goals is to get this down to the sort of depositional environment and thermal history together, to where we're now tying in, seismic data and geologic context, maturity trends from Tmax and other analyses, and building a better picture of that sort of petroleum system across this basin at the end of the day. Okay, so I mentioned earlier in the HAWK system itself. HAWK is the sort of the instrument for the classic pyrolysis, outputting the S1, S2, Tmax, and whatnot. There's also this HAWK PAM method, and the PAM just stands for Petroleum Assessment Method. So this is neat now, where we can, what we call S1, those free hydrocarbons, is very much a broad stroke term. What is really S1? What are those free hydrocarbons? Are they more saturate rich? Are they heavier components? What's the fluid dynamics? How does it flow through the pore systems? How can we think about, mobility is a big thing, and hydrocarbon mobility. So HAWK PAM is just a method to now, instead of kind of doing just a generalized 300 hold and then up to 650 hold, it's much more of a stepwise method, pyrolysis method, where we're really breaking down that S1 component into what's called oil 1, oil 2, 3, and 4. And so obviously your different species of hydrocarbons are going to react differently at different temperatures. And so back to first principles, at the lowest temperatures, only up to 100 C, your most volatile short chain, C3, 4, 5 hydrocarbons are going to evolve from that. Typically oil 1 here is pretty minimal. Oil 2, now we're getting into the C6 to C10 range. So now we're sort of ramping up a bit more. Oil 3, C11 to C19. Now we're going from 100 to 180 and holding. And then oil 4, 180 to 350, and getting some of those more derived, more higher molecular weight fractions out of the oil. Again, from a classic approach, all of these are combined into just that S1 peak. This HAWK PAM method allows for that sort of to pick apart the S1 and be a bit more selective about characterizing that. And so in terms of, again, compound classes, right? Sarah is your saturates, aromatics, resins, and asphaltenes. So your most mobile ones are your sats and aros, and then you need to apply a bit more energy and temperature to the system to get some of those more polar compounds. So in HAWK PAM, we also get this what's called K1. I know it's a bit confusing, but K1 is equivalent to the S2 from classic pyrolysis. And so again, this is now at higher temperatures. This is your source potential. You're breaking down the kerogen and sort of assessing the in this case K1, but you can also get that Tmax from this as well. And this will hopefully explain it a little bit better with some examples. So in this case, we have on the left here, again, a kind of a classic pyrolysis, just our S1, S2 peaks. Here's the temperature ramp where we go to 300 and hold, your S1 comes off, you then ramp steadily up to 600 and hold. And so this is your S2. We see the apex here, we can draw the line at the Tmax and get a sense of the thermal maturity. But when we run this same sample in the HAWK PAM method, we see this S1 sort of, again, break down to the different components. And this, you can see right here, this Tmax is less than 430 or something. This is a immature kerogen, brought about, again, determined by the characteristic of that S2 peak and where it falls along the temperature, the x-axis. Again, just reference and kind of bookmark here for the different fractions. So immature example here, and I think maybe it'll help to show sort of the other end members here with respect to oil window and wet gas condensates. So again, I'll talk about what this S shoulder is, this S2 shoulder is in a minute, but in a more mature, kind of peak oil window sample, we have classic pyrolysis here, high S1 in this case, S2 is here, but you also kind of get this shoulder effect. And so, sometimes this S1, if you have a lot of it, it's hard to essentially get it all out of the rock just at 300 for a few minutes. And so one of the effects of having a lot of S1 is that it kind of starts to leak over into your higher temperatures here, and it creates this what we call shoulder effect on the S2 peak. What that does is it draws the S2 to the left, and that then will give you a lower Tmax and sort of give you a lower maturity interpretation. Not necessarily true, and I'll sort of put a mark in this, and we'll talk more about it later. But when we look at the same sample in the Hawk PAM window, again, now not just going to 300 for 5 minutes or 3 minutes or whatever, we're going to a series of ramps and holds and picking apart this S1 peak to show the oil 2, 3, 4 hydrocarbons within that S1. So for sure, now under these conditions, it kind of helped get rid of that shoulder effect when doing Hawk PAM because of the time and temperature and hold conditions in that versus just the classic time ramp and hold. So on the sort of more extreme example in a very mature system where we have what we call wet gas or condensates, very high maturity fluids or rocks. Right, these are now this S1. When you break down, much more of those, as expected, right? Those light in hydrocarbons, those C5, C6s, C10s. In a more mature system, the sort of thermal overprint has broken down all that organic matter into simpler and simpler components. So you get these sort of wet gas or condensate type fluids from that. And then again, same thing here we see in Hawk PAM. The S2, the generation potential is essentially nil or very low because of that rock has already gone through sort of an extreme thermal gradient and sort of expelled all that it has, more or less. Okay, so I think this is the last example. I think I'm doing okay on time, but this is now trying to switch gears and back to my days at UC Riverside and how I was using TOC and pyrolysis in my research. So, one very important way and useful way to use pyrolysis is as sample screening. So I know a lot of us go out into the field and we collect outcrops, and we're not always working with core and cutting, that's fine. But you can use pyrolysis and TOC as a powerful tool to screen your sample set essentially before you do any more advanced, time-consuming or further work in the lab on those samples. So, simple question I had when I was collecting rocks: are my rocks appropriate for biomarker analysis? And so I want to walk through. I know there's a lot going on, big table. I know you're not supposed to read everything or be. I just wanted to I thought it'd be neat to walk through sort of a real life data set of how we're using, again, pyrolysis and TOC to screen a large data set, look at some key indicators, and then make selections for further analysis. So we do a lot of collaborations with some universities in Iraq. This is from Tikrit University. And so they'll go out, this is mainly cuttings and core, but they'll oftentimes go collect outcrops in the field and send them to us for TOC and pyrolysis. And so what I want to show is just kind of zoom in to some of these zones here. So this also gives you a taste of what kind of the typical output report is of a TOC pyrolysis data set. And so, project ID and sample information here on the left. We have depths and different well name or location, different client IDs, whatnot. The type is important, cuttings versus core versus outcrop all have different pros and cons associated to them. And then everything from here over is the actual output, the digits of the TOC. Remember with TOC from LECO, we're doing that first HCl rinse. And so that gives us the percent carbonate here relative then to the organic carbon. And then all the S1, S2, S3, Tmax, and then you can sort of get these derived ratios by having both pyrolysis and TOC data. So again, first pass for me, I'm looking at what's my TOC, what's my S1, what's my S2, based off S2, what's the Tmax? Are there any sort of funny numbers in here? Does it kind of all fall in line to what we expect with some other context we might have? And then from the basic outputs, you can start to derive some more advanced ratios and equations. Dan Jarvie, had a widely used equation now to where you can convert that Tmax into percent RO. So again, we're not measuring vitrinite in these, but everyone kind of speaks that everyone speaks that language on the RO scale when we talk about thermal maturity. So this helps us again get our bearings on maturity scale. And then again, hydrogen index, for example, does that track with the Tmax or the calculated maturity? Does that track with sort of, again, what sort of the type of kerogen I'm looking at? And so I just pulled out an example. So here's a real pyrogram from this specific example here. This is cuttings. So, what I'm looking at is, this sample has 1.1% TOC, decent TOC. It's got that really high over here, S1 over TOC. And when we look at the pyrogram, we see that it has this low temp shoulder that we talked about. So this is important because what we want to see is we don't just want to view the digits and then just take the digits for face value and then sort of run with those numbers. We want to pair it always with the pyrograms to sort of check that, because this sample for sure has a low temperature shoulder here. What that's doing again is sort of suppressing the S2 peak here, and that's kind of giving you a lower Tmax than what you would normally have, or what you would have if you were to clean up the sample. And so to address this, a very common thing is to just do a solvent wash, an organic solvent. So take that crushed rock, rinse it with organic solvent a few times, do kind of a quick and dirty extraction. Your S1 is your most mobile components, likes dissolve likes. That organic solvent is going to flush out all that S1. And importantly, it's going to flush out this sort of residual effect that's causing this low temp shoulder. S2, right, by definition, is that kerogen component. Kerogen is insoluble in organic solvent. So doing a solvent wash is not going to mess with your S2 peak or your kerogen component. And what that's going to do is essentially drop out the S1. You're going to get rid of this low temp shoulder, and then you rerun the sample, and your S2 Tmax is going to be a bit more realistic or a bit more trustworthy, because it doesn't have this effect on the shoulder effect, kind of pulling it to lower values. So another example from the same data set, also from cuttings now from this different well. This is kind of the other extreme. So now we're 2.4% decent TOC, very low S1. We kind of say like anything less than 0.5 or 0.3-ish is kind of in the realm of the instrument wiggle or variability. But importantly, the pyrogram is matching the data here. In this case, there's low S1, so I don't have to worry about a low temperature shoulder. The S2 is sort of well represented here, and again, because of that, the Tmax is reported 435. Calculated R of 0.67, that kind of early oil window. So that all kind of makes sense. Again, the point I'm trying to make is don't just go off the digits. You always want to ask for the pyrograms to cross-check these data. So moving up the spreadsheet to just another well, this is going to be some of the more extreme examples. So right off the bat, you know, on these from this specific well across a series of cuttings and core, right? We're evaluating with depth, going from shallower to deeper. What I'm seeing here is, okay, my Tmax is 300. You know, most typically you see, you know, values from 430 to 450 or something for an oil window Tmax. And so what's going on with this 317 and you know, the calculated RO from that is 0, essentially. It's such a low value. So again, the power of now bringing in a pyrogram to this is that we're looking at these two samples with very low Tmax. When we look at the pyrogram, oh, okay, that makes sense. The instrument is detecting something. It's just so low and it's such a broad peak that, you know, it has to assign a value somewhere. So, you know, in this case, it's just going to right here and assign in or right here. So for sure, there's S1 in there. You know, my next question then, is that S1 real or is that sort of contamination? And it can kind of be, you know, it can be either or. Oil stained is a term that we say, again, if you're in a reservoir rock that doesn't have a lot of source potential, but there's been oil or fluid that has migrated into that rock, then this would be a typical output. And so we would call this oil stained, and that is a real signal with just no potential in that specific zone. That's fine. The thing to look out though is you know, this can also be a telltale sign of contamination. So if your samples have some sort of oil-based mud contamination, or you have an outcrop that again, maybe you're kind of looking at the outer edge of the rock versus going into the inner parts. This is kind of a telltale sign where we need to think about, okay, is this a real signal or is this contamination? And again, this sort of pyrolysis and TOC gives you the initial interpretation of what that might be, and then you might want to pair it with other analyses down the road. So takeaway is always important to look at your pyrograms alongside your data. So in this exercise, we started with 40 samples. We did TOC and pyrolysis, again, relatively cheap analyses across a larger data set. And that really did help us go to, you know, for sort of each well at different zones from different, you know, in this case, cuttings and core, really select our best candidates for further geochemical analysis. So, you know, it'd be a real pain to without this tool to collect all the 40 rocks and then, you know, do detailed solvent extractions and GCs and biomarker analysis. And then at the end of the day, you get nothing on your biomarkers because there's nothing there. This really helps you screen that data set at the start to select your best candidates and then move forward with some of your other analyses. Okay, just got a few more minutes, I think, with these caveats for what I was talking about with contamination, and then we're at the summary. So OBM, oil-based mud additives, and just contamination in general. You know, again, during my PhD, I worked in you know, neoprotozoic and deep time biomarkers. So very much contamination was at the forefront. And so again, how can you use pyrolysis to screen your samples and look for some of these red flags or these signs that, hey, you might have contamination. Okay, based on that, what do I then have to go do? So additives and OBM and for sure can skew pyrolysis. This is kind of a better drawn example of what I was talking about before from the real data, where in the blue line here, that's kind of the proper analysis where you don't have any overprint or low temperature shoulder on your S2 peak. The red dashed line just shows that when you do have sort of very high S1, whether that's real or whether that's contamination, it can then affect your S2 and sort of push that to the left, again, making you interpret it as less mature than what it potentially really is. And so quite often, again, we'll do, you know, TOC pyrolysis before and after solvent extraction to initially assess it, get an interpretation idea of what's in the system, and then if there are some questionable features, the low temperature shoulders, we'll do a solvent rinse and then run again. And in doing so, that'll fix your Tmax. That'll again make it more realistic to what it actually is, take away the contamination, and give you a better idea of your thermal maturity. So again, just the actual sample that we looked at earlier, here's that low temp shoulder here. So this kind of just, spells out what I was just saying. With high amounts of S1, whether it's real or whether it's contamination, it can pull down that S2 peak. And again, that's just a function of the rate and the temperature ramps that we go through, right? And so you can tackle it with like hot PAM and changing the temperature rates, or you can, if you really want to get rid of it, you do this solvent wash to get a more accurate value. And now your Tmax and your HI, right? HI is S2 over TOC, become a bit more trustworthy, or you can have more confidence in those values versus a sample that has some overprint. Okay, so my last example is just a thought experiment, and didn't want to like for sure like isolate one study or anything like that. This happened in my own time as a grad student too. Again, working in deeper time biomarkers, always have to think about contamination and again, interpretation from multiple lines of evidence. So really, at the end of the day, if you have more sort of these multiple independent lines of evidence that help you interpret that source rock type, that age, that thermal maturity, those should all work in concert, and really that strengthens your story at the end of the day. And so just again, a thought experiment of this is, if you're looking at biomark data from a rock extract, you really should ideally, have TOC and pyrolysis data to at least support those observations and those findings, because in the biomarker world, those compounds are sensitive. Some of those are sensitive to thermal maturity, and so ratios change, and you can get a thermal maturity estimate from biomarkers alone, but you can also get a thermal maturity estimate from pyrolysis data. And so if you have, for an example, an immature biomarker signal coming from a rock that's low TOC, very high maturity, that should be scrutinized a bit, right? We don't want to mischaracterize contamination as sort of a real signal. And so the more data sets you can pull in, and ways to think about maturity in this case, I think the better, and the stronger your story and the more robust your data set will be at the end of the day. Okay, wrapping up now. So again, high level conclusions. Very much program pyrolysis is a routine tool that we use in industry to evaluate that hydrocarbon potential. Again, back to the Band-Aid term, the technique is program pyrolysis, and the offerings are either Rock Eval or Hawk, and TOC is more times than not paired via a LICO instrument. Three main questions and the three key pieces of data that we're trying to get at from this hydrocarbon evaluation is the quantity, the quality, and the maturity. And of course, always look at your pyograms alongside the data. Look out for contamination overprint. Know what to look for. Know some of those different features we reviewed, and always pair the pyrograms with your digits. And right at the end of the day, again, like I said, the more sort of independent lines of evidence you can bring into the story to support your other database or challenge them potentially, I think the more robust and defensible your story is going to be. So that's all I have, and thank you very much for your time, and we'll take any questions.
Sorry, I was muted. Thank you so much. That was really awesome. I really appreciated the demonstration going through how you would screen samples for future biomarker analyses. That was cool. One quick thing that I just wanted to mention, something that I found really useful with these data, is that, as you mentioned, the hydrogen index is going to decrease with increasing thermal maturity. And one thing that we're interested in a lot of our rocks is knowing the original total organic carbon content of a rock. And that can be for just thinking about organic inputs to the rock or metal TOC ratios or whatever in Earth history studies. And if you know the present day TOC and that hydrogen index, there are equations to back calculate the original TOC. And so that's something I found really personally useful in these data. And I point people, there's a recent paper by Hart and Hoffman in Organic Geochemistry that came out that had a really good discussion of why you might want to calculate original TOC. So that's, to me, a really cool thing. Why don't we open up the floor for questions? People can either unmute themselves and ask or raise their hands.